let's talk about limits, because limits are kind of everything really when it comes to calculus. So even though eventually we will move beyond talking about limits, at the very kind of core of really everything we do in differential calculus, where we talk about finding derivatives, every derivative at some very basic granular level has a limit involved with it. We're not always going to talk about that, but we're certainly going to begin by talking about it. Oh, and also let me pin this here so it doesn't look. Yeah, there we go. That's better. So today is the 16th of January. Limits. And so I think first and foremost, we should talk about just kind of the idea about what a limit is. So let's look at this graph. Here's a function, a piecewise function. F of x equal to, what's it got here? Yeah. Equal to x squared plus 1 when x is less than or equal to 0. It's equal to x plus 1 when x is, blew it there, James. When x is bigger than 0 and less than 3. And finally, equal to the square root of x plus 1 when x is bigger than or equal to 3. So we're going to graph this piecewise function. And when I graph things piecewise, I usually just try and graph from left to right. So x squared plus 1 looks like our usual upward opening parabola, but it's been shifted up by 1. So everywhere when x is less than or equal to 0. So when x is equal to 0, 0 squared plus 1 is going to be 1. So I'm going to get the point 0, 1. And then I'm going to have that left side of the parabola y equal to x squared plus 1. And then from 0 to 3, I have the line y equals x plus 1. It's a straight line, slope of 1, y-intercept also of 1, right? If I could plug in 0 for x there, 0 plus 1 would give me 1. So I know if I look at these points, when I plug in 0, I would get 1. When I plug in 1, I will get 2. When I plug in 2, I'll get 3. When I plug in 3, I would have gotten 4. They don't get 4 because this function is defined to be equal to x plus 1 when x is strictly between 0 and 3. So I get this open hole here at the point 3, 4. Just like I get this closed hole here at the point 0, 1. Finally, the last piece of this graph is the square root of x plus 1. So it looks like the usual square root function shifted 1, which way? So 1 to the left or 1 to the right? To the left. So here's what I think about. The usual square root function starts where? In fact, we'll come back, don't worry. Usual square root function starts at, start maybe, okay, right? Technically you could say it starts anywhere, but we think about like going from left to right. It starts at the origin. And then it has this usual shape. You got the point 0, 0, and 1, 1, 4, 2, and lots of other points that are less nice, but those are the ones we often think about plotting. Well, if I want to look at the graph of y equal to the square root of x plus 1, to get the same y value of 0, x has to be 1 less than it was before. Because we're here, if x is negative 1, then y is going to be the square root of 0, which is 0. And if x is 0, y is going to be the square root of 1, which is 1. If x is 3, y is going to be the square root of 4, which is 2. So all of these points are all of those points, but moved 1 to the left. And so adding inside the function always feels a little counterintuitive, because instead of shifting to the right, you actually shift left to counteract the 1 or whatever that you added. So we're not going to get all this though, because our graph doesn't start at -1 or 0 or 1 or 2. It starts at 3. So we're really only going to get everything from the point 3, 2 and rightward. So back to the thing we were at. This graph is going to continue on to the right at the point 3, 2. And it's gonna go like that. Nice, lovely looking graph. Let's talk about some limits of this function f of x. So part A, come on in. What does y approach as x approaches 0 from the left side? Well, if we look at our graph, we can see that as the x values get closer and closer to 0 from the left-hand side, the y values are getting closer and closer to positive 1. You could think about plugging in a very, very, very slightly negative number. So for example, if you wanted to, for example, say what's f of like negative 0.0001. Okay, well, if I'm plugging into this function here, I have to pick the part where the domain is negative. So I pick this first part here, a very, very, very small number squared is going to be essentially 0 squared plus 1, which is going to be 1. I don't really think we need to plug something in to see it. I think we can look at the graph visually and see, oh yeah, the limit as x approaches 0 from the left-hand side of f of x is 1. And again, all that means, and I want to be very, very, very explicit here. As x gets closer to 0 from the left side of 0, the function gets closer and closer to a y value of 1. That's all we mean, yeah. The negative is what's specifying that we are coming in 0 on the left side of 0, or the less than 0 side. Whereas, if I were to write, what's the limit as x approaches 0 from the right-hand side of f of x, using a plus superscript to indicate the right-hand side of 0, or the larger than 0 side of 0, we would then come at it from the other side and say, okay, well, as we approach 0 from the right-hand side, the y values are still also getting close to 1. And since the left, oops, I don't want that, or you can go over here. Since the left-hand limit and the right-hand limit are the same y value, we can then also conclude that since the limit as x approaches 0 from the left of f of x is equal to the same number as the limit as x approaches 0 from the right of f of x, we can then say that the two-sided limit exists. We can say that the limit as x approaches 0 from either side of this function exists and is equal to the same value 1 in this particular case. And that is a thing that is generally true. If you want the limit to exist, the limit from the left-hand side and the limit from the right-hand side have to both exist and equal the same value. There is no other option. Yeah. Let's look at the other interesting point here, which is when, or I should say the other interesting x value, which is when x is equal to 3. And let's look at the limit as x approaches 3 from the right-hand side. So again, looking at my graph, scooch things down just a little bit here. If x is approaching 3 from the right-hand side, the y values are getting closer and closer. I didn't label that point there. The y values are getting closer and closer to a value of 2. If that is the point, 3, 2. Right, again, you can think about substituting a value that's a little bit bigger than 3. For example, if I looked at f of 3.0001, that would be the square root of 3.0001 plus 1, which is about 2. Right, we're getting really, really close to 2. Oh yeah, this is getting really, really close to 2. So as we approach 3 from the right, the limit is 2. Here's where things get more interesting, I think. If we approach 3 from the left-hand side, so the limit as x approaches 3 from the left of f of x. If we look at our function here, if we're coming at 3 from the left side of 3, the corresponding y values are getting closer and closer and closer to 3 plus 1, which is 4. I want to make it extra clear. The limit doesn't care what is actually happening at x equal to 3. What happens at x equals 3 is not of any consequence as far as just the limit is concerned. It is certainly of consequence when we start talking about continuity. But as far as just the limit's concerned, we don't care what happens at 3, but we care what happens near. And near 3, really, really close to 3, like at 2.999999999, well, x is less than 3. And so then the function you're plugging it into is x plus 1, and 2.999999999 plus 1 is 3.9999999. So it's really, really, really close to what? Yeah, 4. Sorry, I don't hear very well, so you have to speak up. Really close to 4. Okay, so the limit from the right is 2. The limit from the left is 4. The overall two-sided limit doesn't exist because the left-hand limit and the right-hand limit are not the same. So we say the limit as x approaches 3 of f of x does not exist. You can certainly abbreviate that as DNE. If it were up to me, I would tell you don't write that it equals does not exist, because it doesn't equal that, it just doesn't exist. So I would write it like this: the limit does not exist. No equal sign is necessary. So I say so a lot. Oh well, I'll get over it. Couple things to emphasize here. Order, maybe, possibly, sure. I never feel like there's enough room up here. Probably my own problem though. So here's what I would say. Yeah. If the limit as x approaches c from the left of a function is equal to L, and the limit as x approaches c from the right of the same function is also equal to the same value L, then the limit as x approaches c of f of x is equal to L. And vice versa. Meaning the opposite implication is also true. If the limit as x approaches c is equal to L, then the left-hand limit and the right-hand limit both had to equal that same L value. It's actually usually phrased as an if and only if statement. If the first thing is true, then the second thing has to be true. And if the second thing is true, then the first thing has to be true. Okay. Yeah. Yeah. Sure. So let's look at some more examples. Let's look at another piecewise function that we're not going to graph. Piecewise functions, so by the way, piecewise functions are really nice for exploring limits because there's a lot of discontinuity that we can just make up easily. Whereas many functions on their own that we see, like trig functions, like polynomials, are usually pretty continuous everywhere. So that's another great use of piecewise functions. Let's look at this function g of x. Let's say g of x is equal to x cubed plus 2x when x is less than 1. The cube root of x plus 5 when x is bigger than or equal to 1 and less than or equal to 8. And finally, it's equal to x minus 1 when x is larger than 8. And I'm going to ask about, let's ask, what is the limit as x approaches 1 of of g of x. Sorry, it's a g, not an f. To answer a limit question like this, where you can see that the function is defined to be something different on the left of 1 than it is on the right of 1, we have to look at both sides. There's no other choice. So we're gonna look at both sides. We're gonna ask ourselves, well, to answer this, first, let's look at the limit as x approaches 1 from the left-hand side of g of x. Okay, which piece of the function do we have to use? The top piece, the middle piece, or the bottom piece? Good question. Well, if we're approaching, what side of 1 are we on? The left. So if we're on the left side of 1, we are less than 1, and we need to use the piece where x is less than 1. So we're using this top piece. So that's going to be the limit as x approaches 1 from the left of x cubed plus 2x. And here's what we're going to come to see is a pretty typical thing we do with limits. We're often just going to substitute in the value that x is approaching. And then if you get a real number, great. What we're really doing in practice is we're saying, well, if x is really close to 1, like 0.99999, and you plug it in, you get 0.9999 cubed, which is almost 1, plus 2 times 0.999, which is almost 2, and almost 1 plus almost 2 is almost 3. Or in other words, plug in 1 and get 1 cubed plus 2 times 1, which is 1 plus 2, which is 3. So normally, if you can plug in the value x is approaching and get a real result, that's good. That's usually what the limit is equal to. Occasionally someone can make something up where it's not, but okay. Then we have to look at the other side of 1. We'll look at the limit as x approaches 1 from the right of g of x. Now I have to use the piece of the piecewise function where x is bigger than 1, but not too much bigger than 1, right? We don't want to use this bottom piece where it's equal to x minus 1 when x is larger than 8. That's not going to get close enough to 1. We have to use the piece where x is just bigger than or equal to 1. So this middle piece. That's going to be the limit as x approaches 1 from the right of the cube root of x plus 5. And if we plug that in, so if I plug in 1 for x, that's the cube root of 1 plus 5, which is 1 plus 5, which is 6. And those aren't the same. 3 and 6 are not the same number. That means the limit as x approaches 1 of g of x does not exist, because the limit as x approaches 1 from the left is equal to 3, and that's not equal to the limit as x approaches 1 from the right, which is 6. You probably don't need to write all this explanation out on the bottom here, but that is why this limit doesn't exist. The left-hand side and the right-hand side are not the same value. Why don't you all try finding both the limit as x approaches 8 from the left and the limit as x approaches 8 from the right. With the same function, find or figure out what's going on with the limit as x approaches 8. So you'll have to do both the limit as x approaches 8 from the left and the limit as x approaches 8 from the right. They're right bigger? Is that visible enough? If I'm writing too small, you can always let me know. Sometimes I start trying to cram stuff in the margins and I should just use more paper. I have plenty of paper. All right, so you could just write the answer here, but I would really prefer everyone, when you're doing a problem like this, to write the next step, which is to write the limit as x approaches 8 from the left, and then fill in the correct piece of the function that we're going to take the limit of. In this case, it's when x is just a little bit smaller than 8, which is right here where x is smaller than 8. So that's going to be the piece where g of x is the cube root of x plus 5. Then we plug in 8 because we can. We get the cube root of 8 plus 5. What's the cube root of 8? 2. And 2 plus 5 is 7. On the other side, we have the limit as x approaches 8 from the right-hand side. And now the piece we want to use is the piece when x is larger than 8, which is when g of x is equal to x minus 1. If we plug in 8, we get 8 minus 1, which is 7. And since those two limits are the same value, the limit from the right and the limit from the left, we can say that the limit as x approaches 8 of g of x is equal to 7. It exists. So usually with piecewise functions like this, when you're looking at a limit, you have to look at a limit from either side, because most of the time you're going to be asked about the places where you change from one piece to another. That said, someone could totally ask you, for this same function, what's the limit as x approaches 13 of g of x? Well, then there isn't really an issue here, right? When x is 13, well, when x is bigger than 8, this function is x minus 1. So whether you're on the right side of 13, like 13.1, or on the left side of 13, like 12.9, you're still way, way right of 8. And you still get to use this piece regardless of which side of 13 you're on. So we don't really have to look at the double side limit here. We can just say, well, we know that when x is getting close to 13 on either side, the function is going to be equal to x minus 1. And then if x is getting really, really close to 13, x minus 1 is getting really, really close to 13 minus 1, which is 12. That's why we're kind of allowed just to plug in the value x is approaching. You're really just saying, oh yeah, my function is x minus 1. If x is close to 13, the function gets close to something that is 1 less than 13, because that's how math works. But of course, it's not always going to be this easy, right? We're starting off with examples that make sense so that we can talk about left and right, but eventually we're going to get to examples where it's more computationally challenging. Let's look at, not quite that yet. No, where'd you go? Sorry, I keep losing my pages here. Yeah, a few more pages. So let's say, oh, good job. So, interesting. Where did you come from? Sorry. Sometimes I have old paper and like just writing and stuff. Let's look at the limit as x approaches 3 of x squared plus 4x plus 3. There's nothing terrible about this. We can just say, well, okay, x is getting close to 3. So x squared is getting close to 9. 4 times x is getting close to 12. And 3 is just 3. So we're going to get 3 squared plus 4 times 3 plus 3. Which is 9 plus 12 plus 3, which is 24. Graphically, what happened was, sure. We had something that looked kind of like this. Here's my parabola, my upward opening parabola. And when x got closer and closer to 3, the y values got closer and closer to 24. Like that. And we didn't worry about which side, because we knew this function was defined to be the same function on the right of 3 as it was defined to be on the left of 3. Something else worth mentioning here is I used a bunch of limit laws when I did this limit. I didn't say any of that, and normally you're not going to expressly communicate that you have used limit laws. But I'll just point out that when I did this, if I really wanted to kind of talk about the limit laws, and we'll kind of come back to this a little later, is I could have said the limit as x approaches 3 of x squared plus 4x plus 3. When you have the limit of a sum, you can really write it as the sum of the limits. So it's really the limit as x approaches 3 of x squared plus the limit as x approaches 3 of 4 times x plus the limit as x approaches 3 of the constant 3. Now 3 was a bad choice here, sorry. What's the limit as x approaches 3 of any constant? Just that constant. So no matter, right, if you think about this, if you think about the line y equals 3, which looks like that. And then again, 3 was a bad choice here because, right, the 3 could be a little confusing. It could be, x could be approaching 2 or 1 or whatever. The limit would still be 3. But if y equals 3, it doesn't matter what x is approaching. It could be 3 or 4 or anything. The y values, I wouldn't even start getting closer and closer to 3. They're just 3 the whole time. So as x gets close to whatever it's getting close to, the y values are staying at a constant value of 3. So the limit law is that the limit of a constant is just going to equal that constant. That constant. Just to be extra clear. Okay, and then the limit of x to a power is just the number to that power. That's going to equal 3 squared. There still is a limit law I have to apply here, which is pulling the constant multiple out in front. It's going to be plus 4 times the limit as x approaches 3 of x, plus this part we said was 3. And finally, we have 9 plus 4 times the limit as x approaches a number of just that number is 3. Sorry, I said that slightly wrong. The limit as x approaches the number of x is just the number it's approaching, which makes sense, right? You're saying, what's the limit as x approaches 3 of x? Or what is x getting close to as x is close to 3? It seems like I've already said the answer. X is getting close to 3. And then finally, another 3 here. So 9 plus 12 plus 3 is 24. So when someone asks you maybe once or twice to use or show all the limit laws you've used to show a limit, that's what they mean. Do we ever do this in practice? No, we don't do this in practice. It's tedious and it's beyond unnecessary. But the idea is that these limit laws, which we'll talk about more in a bit, are underlying everything that we're doing with limits. We're breaking up limits with addition or subtraction or division or multiplication because we can. But we're not usually saying that we have done so. And most of the time, it just amounts to plugging it onto some expression. Okay, let's look at the examples that start to get a little bit more interesting. Let's say we have the limit as x approaches 2 of x squared minus x minus 6 over x minus 2. And you're going to see a lot of this when I try to plug into it and ask, okay, what's this function getting close to? Is x is getting really, really close to 2? Well, it's getting really close to 4. Oh, I made a mistake. That's all right. Minus 2. I really don't want to do this limit though. It's not where I meant to go. I meant to, let's fix it. It's supposed to be a plus. Sorry about that. Sometimes mistakes are made. Don't worry. We'll see these types in a little bit, but not right now. When I plug in 2, I get 4 plus 2 minus 6 over 2 minus 2, which is 0 divided by 0. And what's 0 divided by 0? Good question. It's anything you want it to be. Really? How many times does 0 go into 0? 5. 5 times 0 is 0. 0 minus 0 is 0. Yeah, 0 remainder. I'm good to go. But obviously I'm kidding, right? Or not, I mean, not so much kidding is that it can be anything, but specifically it's going to be the one thing it actually needs to be for this limit to be what it is. But you could have said 50 or 1,000 or 17 and the division would still work. This is why we call 0 over 0 an indeterminate form. It's more than just being undefined. Indeterminate form means it could end up taking on any value. any real number, or it could end up being some sort of infinity, which again is not a real number, but we're not worrying so much about that right this moment. So what this really means for us in practice is we have to do more algebra typically. So usually that's going to mean either factoring and canceling, or multiplying by a conjugate first and then factoring and canceling, or getting a common denominator and then factoring and canceling. There's almost always going to be some factoring and canceling. Here's the good news. The question? Yeah. Yeah. I mean, so I'll say it's not 100% all the time an option. Like later on when we talk about the limit as x approaches 0 of sine of x divided by x, you can't factor anything out there, but there's a way of dealing with that that's a totally geometric argument. But a lot of time, yeah, if we can factor and cancel, we want to. Now, here's the good news. We plugged into and we got 0 on top. That means that x minus 2 has to be a factor. You have no other choice. It's literally the fundamental theorem of algebra. It says that if you plug in a number, a real number, to a polynomial, which x squared plus x minus 6 is, x minus that number has to be a factor. It's kind of cool. We'll see another example here in a minute here. But what that means for me is I know right off the bat that x minus 2 has to be a factor, which also makes it really easy to find the other factor, because I know that x times x is the only way I'm going to get the x squared in front, and that negative 2 times what is going to give me negative 6. Right. So if you know one piece of the factoring, the finding the other piece is almost usually really easy. And then on the bottom, I still have an x minus 2. And then I would encourage you all to say that x minus 2 divided by x minus 2 is 1. Is it always 1? He's like, why would you ask this question if it wasn't? Well, yes, except for when. When would that be a problem? When x is 2. Okay, here's kind of the crux of limits. Does x equal 2? No, what's x doing? It's getting really, really close, but not equal to 2. That's why we're allowed to do this. Because as long as x isn't 2, it's not, then x minus 2 divided by x minus 2 is always a not 0 number divided by the same not 0 number. If x is 17, then you have 17 minus 2 divided by 17 minus 2, which is 15 divided by 15, which is 1. And it doesn't matter what you pick for x, as long as you don't pick what? Right. And we can't pick 2, because that's expressly what the limit means, is we are getting as close to 2 as you like, except you don't actually get to 2, which is great. It means it works exactly how we need it to work. So what's going to happen here is we're going to say this is equal to the limit as x approaches 2 of x plus 3. And then plugging in 2, we get 2 plus 3, which is 5. Let's look at this graphically for just a second. Even though we don't really need to, we found the limit without using a graph. I want to show you the difference between these two functions. So we've got this function, f of x equal to x plus 3, which is kind of the simplified version, which I'm going to graph. It has a y-intercept of 1, 2, 3, has an x-intercept of negative 1, 2, 3. Here's my f of x equal to x plus 3. Wow, I didn't do a great job of drawing it. And I'll point out that this graph has the point 2, 5. But then the thing we actually looked at, which was x squared plus x minus 6 divided by x minus 2. The only difference between these two functions is that there's a domain issue. This first thing I wrote has domain everything, right? There's no problems. There's no potential division by 0. There's no square roots. There's no logarithms. This function is obviously undefined when x is equal to what? 2 again. So, but everywhere but 2, as long as x isn't 2, this function is equal to x plus 3 as long as x is not equal to 2. So these functions look the same everywhere except that this function at 2 has a hole. drawing there is less than excellent. We have the same points, 0, 3 for the y-intercept, -3, 0 for the x-intercept. But then right here, where this graph has the 0.2 comma 5, this graph does not have the 0.2 comma 5. It has all these other points that are really, really close to it, like 2 point lots of zeros 1 comma 5 point lots of zeros 1. But we don't have the 0.2 comma 5. The limit still exists. The limit doesn't care what's happening at 2. The limit just cares what's happening really close to 2. Do you need to know all this closeness stuff to really kind of be able to calculate limits? Probably not. Is it good to know about it because this is what the crux of all what we're doing is about? Yeah, it's good to know that you're really thinking about what's happening to the y values as x is getting super duper close to whatever x value we have picked. What's actually happening at that point does not matter. Taking 1 second, taking one step further, it will matter once we start talking about whether or not this function is continuous at 2. The left-hand function is definitely continuous at 2. The right-hand function is definitely not continuous at 2. It's not even defined at 2. But that's not what we're talking about with the limits right now. Question?
What does it look like to actually write the proper answer to this problem? Is it that limit of x approaching 2 is
Yeah.
x plus 3?
Yeah, so if I was writing the answer, I would write this work here.
Gotcha. All of
Yep, all of that.
Okay.
Let's look at a few more examples. So okay, and in general, you never have to tell me anything. You just walk out, you're good to go. Yeah, and I'll post this as soon as yeah.
Sure.
And in general, that's true for everybody, right? If you need to go because you have a class, or you need to come in late because you have a class, totally fine. Just do as you need to. So yeah, let's look at this example. Let's look at the limit as x approaches. Sure. Yeah. 3 of ouch. Sorry, let me think here for a second. Yeah. 3 of 4x squared. Yeah. Sorry. Minus 11x minus 3 over x squared minus 9. Some words of wisdom. Most of the time, it's a pretty good bet that you're going to get 0 over 0. You should still check. Because invariably, someone's going to throw one in there where it's like 0 on top. And if you don't look at it quite right, it seems like it could be 0 on the bottom, but it's actually like 5. So because 0 divided by 5 is just 0. 0 divided by 0 is indeterminate. So definitely don't write it down, but do the mental check. If I plug in 3, 3 squared is 9, 4 times 9 is 36, minus 33 is 3, minus 3 is 0. On the bottom, 3 squared minus 9, and 9 minus 9. Okay, so I do get 0 over 0.
what happens if we don't get 0?
Well, it depends. Depends on, so as long as you get not 0 on the bottom, whatever the number is your answer. Specifically, the other situation that's problematic, which we're not there yet, but will, is that if you have not 0 over 0, that's when you have other problems. This is undefined, and there's more to say about that, but we're not there yet. Yeah, in fact, yeah, we'll look at some more examples here. So let's see. If I plugged in 3, I knew I was going to get 0 over 0. So that means both in the numerator and the denominator, what should we have as a factor? Okay, great. So we know that x minus 3 is going to be a factor in the numerator, and x minus 3 is going to be a factor in the denominator. Fill in the rest. Factor, the denominator should be pretty straightforward. The numerator is not too hard to figure out if you apply the same sort of logic we applied for the previous problem. Think about what needs to go there to multiply the 4x squared, and what needs to go there so that you multiply the -3. So here's the thought process. What do I need to multiply by x to give me 4x squared? 4x. It's the only way. What do I have to multiply by -3 to get me -3? I know it sounds like it. And that works. Since I know x minus 3 is a factor, I know this is the other factor. Now we can check if we want to. If you want to go over here and FOIL it out, x minus 3 times 4x plus 1, that's going to be x times 4x, x times 1, -3 times 4x, and -3 times positive 1. And that's going to be 4x squared, x minus 12x is minus 11x minus 3. Oh, that's exactly what I had in the numerator there. So I'm saying is, you don't have to think too hard about how this trinomial factors if you already know one of the factors. The other factor is really easy to kind of reconstitute from what we know has to be true. In the denominator, it should be x minus 3 times x plus 3, like a usual difference of squares would factor. And then we can not cancel, but divide. X minus 3 divided by x minus 3 is still 1, because x isn't 3, because we're getting close to, but not equal to 3. And then that's going to equal the limit as x approaches 3 of 4x plus 1 over x plus 3. Notice I'm writing the limit as x approaches 3 in every step until I actually find the limit and say, okay, now I'm going to actually substitute in the value of 3 for x and write 4 times 3 plus 1 over 3 plus 3. And I no longer write the limit because I'm actually finding the value. And then I simplify. 12 plus 1 is 13, equals 3 to 6. And that is the actual answer to this question. All right. Yeah, you guys do the next one. Try this one. The limit as x approaches 2 of 4x squared minus 3x minus 10 over, sure, 6x squared plus 12x. So hopefully everybody tried plugging in 2 before they started just factoring things. So I just plug in 2. In the numerator, I get 0, 16 minus 6 minus 10. In the denominator, I don't. And 0 divided by not 0 is just 0. So this limit is 0. And that's kind of what I mean by sometimes people will do something kind of tricky. They'll give you a limit that looks like you maybe had to factor and cancel stuff, but really if you just plugged in what x is approaching, you get the number that is the limit. Now, the question I really was going to ask, but then I changed the last moment, was what's the limit as x approaches 2 of almost the same thing, except the denominator has a minus sign. So it's really the limit as x approaches 2 of 4x squared minus 3x minus 10 over 6x squared minus 12x. And now you can see that if you do plug in 2, you do get a 0 over 0 type. Meaning, yes, now you have to factor. So go ahead and try that one. And I will say, even though you know that x minus 2 factors out from the denominator, it might be easier for us to just factor out a 6x. That's what I would do if I was factoring the denominator. So go ahead, try and factor and cancel, factor and divide things to 1, and then find what the limit is. I believe you should get 13 over 12. That's a good question. I don't know if there is a good name for that.
I'm trying to write up step by step.
Yeah.
It's a little funky.
Because, right, the value that we get is the limit value if it exists, but
Yeah.
I don't know. Yeah, I don't think I've ever seen a name for the value that we typically call it A,
Oh, okay.
but like, or either A or C, depending on the textbook. But yeah, in fact, yeah, we'll say more about that in a second here. Okay, so I know that x minus 2 should be a factor. That's helpful for the numerator. I don't feel like it's super helpful for the denominator. For the denominator, I would note that both 6x squared and 12x have a factor of 6 and a factor of x I can pull out. When I pull out the 6x, I'm left with an x there and a minus 2 there. To me, that feels easier than trying to factor out the x minus 2 and seeing what's left over. So sometimes it's easier to do the thing that just naturally occurs to you. In the numerator, x minus 2 certainly factors out. And then I have to have a 4x times x to give me 4x squared, and a plus 5 times negative 2 to give me negative 10. There's no other way. You can check the middle terms if you want. The middle terms added to negative 8x and positive 5x, which gives you a negative 3x, which is what we need. All right. Simplify. X minus 2 divided by x minus 2 is equal to 1. So I have the limit as x approaches 2 of 4x plus 5 over 6x. Plug in the 2 and get 4 times 2 plus 5 over 6 times 2, which is 13 or 12. So just as a reminder, 0 over 0 can be anything. It can be 13 over 12. It can be 5. It can be whatever the previous limit was. It just depends on what type of limit expression we happen to be looking at. Bless you. Not everything is just going to be factoring and canceling. There's typically 2 other kind of standard kind of varieties of algebra things we have to do. One of them is multiplying by the conjugate. So let's look at some other examples. Let's say we have, why do I keep feel like I'm just gonna keep putting things under other things here. Yeah. Okay. So bent paper is not doing it for me. Let's try the limit as x approaches -5 of the square root of x plus 14 minus 3 over 2x plus 10. I do a quick mental check. -5 plus 14 is 9, square root of 9 is 3, 3 minus 3 is 0, and in the bottom, -10 plus 10 is 0. So I definitely have a 0 over 0 type. I don't think I need to write that down, but you can certainly. In fact, I will. But normally, if I was like taking a test, I would just observe in my brain that it was 0 over 0 and then start doing the work. So I don't want to write more. I don't want to write this whole expression again on an exam if I don't need to. To deal, so here's the problem. Unlike the previous ones, I can't just factor out an x minus minus 5 or an x plus 5. I can in the bottom. At the bottom, I can write as 2 times x plus 5. But in the numerator, I don't have a polynomial. Excuse me. I don't have nice positive integer powers of x. I have a x plus 14 all raised to the 1/2 power. Not a polynomial. Can't say that x plus 5 or x minus minus 5 is a factor without doing some work first. And the work here that is typical is to multiply by 1. Specifically, one that is the conjugate of the square root thing divided by the same. So I'm going to multiply by the square root of x plus 14 plus 3 over the same square root of x plus 14 plus 3. We're multiplying by the conjugate, specifically the conjugate of the root part. Technically, 2x minus 10 is also a conjugate. It's just the conjugate that we don't need. All right, why do we do this? Because it simplifies nicely. When you multiply something by its conjugate, the middle terms cancel out. Right? You might know it more better. You might know it. Is there a, am I trying to, is it better? Sure. You might have seen it before as something like this. A minus B times A plus B. We are multiplying conjugates together. And we're getting A times A plus A times B minus B times A minus B times B. But A times B and B times A are the same. And so A times B minus B times A is 0. I should say that they're together, they're 0. So we end up with just the first thing squared minus the second thing squared. And that's always what's going to happen when you multiply two conjugates together. Because you get the first thing squared, middle terms cancel, and then the last thing, you get minus the last thing squared. So here, we're going to get the limit as x approaches -5 of, I'm going to write it out kind of annoyingly, the square root of x plus 14 squared minus 3 squared. And then the denominator, you don't multiply out. Or I should say, the things that aren't conjugates, you don't multiply out. So I'm going to factor out the 2 from the bottom and write that as 2 times x plus 5. But then I'm just going to leave this square root of x plus 14 plus 3 as is. It's definitely not in our interest to multiply those out. Simplify. We have the limit as x approaches -5 of x plus 14 minus 9 over 2 times x plus 5 times the square root of x plus 14 plus 3. And then the numerator simplifies to x plus 5. Then x plus 5 divided by x plus 5, or the problem pieces are going to get dealt with. X plus 5 divided by x plus 5 is just 1. So we have the limit as x approaches -5 of 1 over 2 times the square root of x plus 14 plus 3. And then we can plug in -5 for the remaining x's. We get 1 over 2 times the square root of -5 plus 14 plus 3, which is 1 over 2 times 3 plus 3, which is 1 over 12. Kind of a bit of work. Happens. Questions about this example? Yeah.
So it's the same rule that there always has to be an x plus 5 to cancel.
Right. Eventually, we're going to need the x plus 5 in the denominator, which is giving us a division by 0, to divide out with some x plus 5 in the numerator so that we get those being 1. Or sometimes, in fact, we'll see this in the next example. Let's look at another example of this. So I have limit as x approaches 4. Sure, let's make it not terrible. X minus 4 over the square root. Yeah, that's what I wanted. No, I didn't want that. Sorry, ignore the square root. Sorry, I'm blowing it. Making things up on the fly. We want X minus 4 over, yeah, we want, sure, let's say 5 minus the square root of 21 plus X. Quick check. If I plug in 4, yeah, I get 0 over 0. So now, what's the conjugate we have to multiply by?
5 plus square root.
Yeah. So both in the denominator and in the numerator. Okay, there's something kind of funky that happens here. So I still have the limit as x approaches 4. The numerator just stays as x minus 4 times 5 plus the square root of 21 plus x. And the denominator, just like before, when you multiply conjugates together, we get the first thing squared minus the second thing squared. And this is where I really do encourage you to write it out as the square root of 21 plus x squared. Here's why. If we continue, we end up with still x minus 4 on top times 5 plus the square root of 21 plus x. On the bottom, we have 25. Watch the mistake. Minus 21 plus x. It's a mistake. I don't have minus 21 plus x. I have minus all of 21 plus x, which means I have to distribute the minus sign. Also, if I didn't have that parentheses there, I would have ended up with 25 minus 21, which is 4. And 4 plus x and x minus 4 are not the same. They don't divide out. They give me 1. They're totally different. So it's problematic to miss that parentheses here. So simplifying this way, we have the limit as x approaches 4 of x minus 4 times 5 plus the square root of 21 plus x over 25 minus 21 is 4, and the minus sign distributes there, you get 4 minus x. Ooh, those don't look the same. X minus 4 and 4 minus x. Not the same. But at least x isn't 4, right? It's just approaching 4, so it's not 0 over 0 until you plug it in. What happens when you divide things like that? What's 7 minus 4 divided by 4 minus 7? Three divided by negative 3 is? What's 19 minus 4 divided by 4 minus 19? Also negative 1. When you subtract things in the opposite order, you get the same value, but they change signs. I could pick any number in this first spot. It could be 37. And I don't know, I mean, okay, fine, I do. 37 minus 4 is 33. 4 minus 37, I'm pretty sure is negative 33. Number divided by the opposite of that number is always going to be negative 1. So when you subtract things in the opposite order and divide them by each other, you end up with a negative 1, which is the fast way of doing it. If you don't like that, you can simply factor out a negative 1 from the top or from the bottom. If I want, I could write this as the limit as x approaches 4, leave the x minus 4 on top as is. On the bottom, factor out a negative 1. And then if I divide out by negative 1, 4 divided by negative 1 is negative 4. And negative x divided by negative 1 is positive x. But negative 4 plus x is the same as x plus negative 4 or x minus 4. So that, I should say that divided by that will be 1, but then there's a negative 1 out in front. So either way, you're getting the limit as x approaches 4 of negative 1 times 5 plus the square root of 21 plus x. In this version, this divided by that was equal to negative 1. In this version, we factored out the -1, and then this divided by that was just 1. And I put it in the top because dividing by -1 ends up being the same as multiplying by -1. Right, I just didn't want to write it in the denominator because I was lazy. And then we can plug in for x and get -1 times 5 plus the square root of 25, which is -1 times 10. This comes up relatively often, this like x minus 4 divided by 4 minus x kind of thing. So it's good to get comfortable with it, be like, oh yeah, if we subtract in the opposite order and divide, we just get -1. It's also good to know that when you subtract things in the opposite order, you do get the opposite value of what you had before. And it does come up kind of frequently actually in 21B. So there's often times where you're like doing an integral of a thing and then you do the integral of the thing, but the order of subtraction is reversed. So it's worth it. Okay, couple more algebra things, then we'll talk about how much time we got. Never enough. There's never enough. We'll try to get through the limit things that we can here. Let's look at the following limit. Let's take the limit as x approaches 3 of 15 over x minus 5 over x minus 3. X minus, yeah, that's right, yeah. Is that 0 over 0? Yes, definitely. We're good to check. Also good to make sure your 5s look like 5s and your 3s look like 3s. Sometimes that 5s kind of get a little bit sloppy. Okay, so when you have fractions and fractions, we typically need to get a common denominator. So for this one, I would rewrite this as the limit as x approaches 3 of 15 over x minus 5 over 1. And then I would multiply the 5 over 1 by x over x. All divided by x minus 3. And then I would rewrite the numerator as 15 minus 5x all over x. And then instead of doing what I'm about to do, writing it as divided by x minus 3, I would say, well, dividing by x minus 3 is the same as multiplying by 1 over x minus 3. Right? Because that's really x minus 3 over 1. When you divide by a fraction, you end up multiplying by its reciprocal. I don't want to multiply out the bottom. I already have the piece that I'm trying to get rid of. The x minus 3 is the piece that I want to divide out. So I need to find it somewhere else as well so that I can have the division happening. What can I factor out from the numerator that's going to help me achieve that? Sorry, I'm deaf. I couldn't hear you. Think I heard 5? Okay. 5 is an excellent choice. There's probably even a slightly nicer choice if we really wanted to look for it. I might pick -5. Actually, honestly, I would probably pick 5 to be perfectly honest. But -5 is the one that's I think easier in the end. So you factor out a -5 from the top, you're left with -3 plus x over your x times x minus 3. And those are the same. I know they're written not the same, but they are the same. You really like, you can rewrite it as the limit as x approaches 3 of -5 times x minus 3 over x times x minus 3. X minus 3 divided by x minus 3 is in fact 1. So we're left with, you could probably skip this step and just say you have -5 divided by 3. So when it comes to limits, if you have these, in fact, let's just say the words, James, let's write them down. When it comes to limits, here's what I would say we typically try to do if we can. So for limits, the first thing you want to try for the limit as x approaches a of f of x is just plug in whatever x is approaching. And if you get a real result, then you're done. Like, for example, the limit as x approaches 4 of x squared plus 7 over x minus 9. Yeah, this would be a problem if I was approaching 9. If I'm approaching 4, I can just plug in 4 and get 4 squared plus 7 over 4 minus 9, which is 16 plus 7 over 4 minus 9. That's it. If you can plug in whatever x is approaching and get a real number, great. That's typically your answer. There are some small exceptions to that if you have weirdly piecewise defined things, but for quote unquote normal looking functions, again, normal is right a word full of meaning, but for functions that look not abnormal, usually this works just fine. But most of the time, that's not gonna happen. Right? You're not, no one's like, maybe once on your exam, but most of the time it's going to be like a 0 over 0 or a not 0 over 0. So if you get 0 over 0, there's a few things to do. Typically, what I say is we do some algebra. You can either try to factor and cancel. Or if you see a square root, use a conjugate. Or if you see some fractions and fractions, get a common denominator. Those aren't the only things that we do when we have 0 over 0, but they're the first things we try if things look relatively algebraically manipulatable. If you can manipulate things algebraically, these are the things to try. It's not always going to work. For example, there are things where this will not work, like, sorry. The limit as x approaches 4 of the absolute value of x minus 4 over 2x minus 8. If you plug in 4 here, we get 0 over 0. Now the problem is we can't factor and cancel here. I really want to make that extra clear. If I try to do this as the limit as x approaches 4 of the absolute value of x minus 4 divided by 2 times x minus 4, those aren't the same. The absolute value of x minus 4 divided by x minus 4 doesn't necessarily equal 1. It does some of the time. Some of the time it equals -1. Right? If x was, say, like 0, what's 0 minus 4? And what's the absolute value of 0 minus 4? And 4 divided by -4 is -1. So we actually have to do a lot of the time for these ones involving absolute values is look at either side of what makes it equal to 0 or whatever we're approaching. So typically this involves breaking it up into the limit as x approaches 4 from the right hand side. Okay, and this is actually when it becomes really important to be able to express the absolute value as a piecewise function. So if x is bigger than 4, then x minus 4 is positive. And the absolute value of something positive stays as it was, right? If you're taking the absolute value of 5, you just say, oh, I get 5. So if the insides are positive already, we can just drop the absolute values. And then x minus 4 divided by x minus 4 is 1. So left with the limit as x approaches 4 from the right of 1/2. And the limit of a constant is the constant. On the other side of 4, on the left side of 4, now x minus 4 isn't positive. X minus 4 is negative. If x is less than 4, which it is in this limit. What do you do with the absolute value of a negative number? Like, how do I, like, I know the absolute value of -5 is 5, but like, how do I turn -5 into 5? You're like, and you don't just you just drop the minus sign. That like, how do I do it mathematically? I multiply it by -1. Because that'll work for any negative number I'm trying to take the absolute value of. -6, oh, I'll get -6, which will be +6. So if I want to take the absolute value of something that I know is already negative, it's the negative of that thing that is already negative to make it something positive. Let me ask you all, if x is less than 4, and I haven't written the bottom part yet, but if x is less than 4, is that numerator positive? You pick a number less than 4. Anything you like, 3, -30, anything. If you plug that in for x and then do whatever's written on top, you're going to get something positive. That's the right thing to do. And then if we write in the rest of it, x minus 4 divided by x minus 4 is still 1, but now I'm left with a -1 on top and a +2 on the bottom. So you have the limit as x approaches 4 from the left of -1/2, which is equal to -1/2. So this limit doesn't exist because the left-hand side and the right-hand side are not the same. The limit as x approaches 4 of the absolute value of x minus 4 over 2x minus 8 is equal to, I don't like to write equals to, does not exist. It's not like a crime to write equals does not exist. I just feel like it's simple. Graphically, here's what's happening. There's 4, and on the right side of 4, this function is equal to +1/2. On the left side of 4, this function is equal to -1/2. And at 4, it's totally undefined. But the right-hand side and left-hand side are clearly not approaching the same value. Also, the way we're doing, I didn't actually write down the piecewise function, but we could have written down the piecewise function that says that the absolute value of anything, x minus 4 in this case, the absolute value of anything is equal to the thing inside the absolute value if the stuff inside the absolute value is positive. And it's equal to the negative or opposite of that if the stuff inside the absolute value is negative. And that's what we did. We just didn't write it or think of it quite like that. We thought of it as x minus 4 if x is bigger than 4 and negative x minus 4 if x is less than 4.
Do absolute value functions ever happen?
Yes, definitely. I mean, right, I could have taken the limit as x approached anything else other than 4 here. Like it feels kind of like a non-issue, but if I had said like what's the limit as x approaches 7 of the absolute value of x minus 4 over 2 times x 2 times x minus 4, then I'm just going to get 3 over 2 times 3, which is 1/2. Most functions have limits that exist almost everywhere. Just like most functions we're going to see are going to be continuous almost everywhere. It's just that there's a few points of particular interest where things might not be continuous or where a limit might not exist. But like if you look at this function I graphed, this function is pretty nicely defined almost everywhere. But there is one point that's kind of a big problem. So that's kind of what we mean. I still got a couple minutes. I guess if you need to leave early, you're always welcome to go early. I'm gonna stop. I'm gonna talk until 2:30 because I can. Because I want to say one more thing. Yeah. So there's so many more things to say though. Here's the last thing I'll say. So the one kind of limit we didn't talk about was if you have a one of the types of limits we didn't talk about was not 0 over 0. Also, for those of you, I don't know if McDonough's going to cover it. I guess I hope he does. I know Oberschelp has already started talking about the delta epsilon limits or the precise definition of the limit. We will talk about that. Hopefully McDonough also does, just so that we're all kind of having parity as far as where we're at. But we'll probably do some of that next class. What I want to talk about lastly was limits of this type for one quick moment. Limit as x approaches, say, 3 from the right of 2x over x minus 3. So here, if we are to plug in 3, what are we going to get? Well, we're going to get 0 somewhere. Right. We're going to get 0 in the bottom and 6 in the numerator. And division by 0, I should say not 0 divided by 0, is not an indeterminate form. It actually is undefined. But we can be more precise about the way in which it is undefined. Here's what I mean. Pick a number really close to 3, but it's slightly bigger than 3. So let's say that x is like 3 plus 1 over 1,000. If I plug that in, 2 times 3 plus 1 over 1,000 over 3 plus 1 over 1,000 minus 3. Well, the top is still essentially 6. Okay, it's like 6.0002. But the bottom, the 3 minus 3 is 0, is just 1 over 1,000. What is 6 divided by 1 over 1,000? Well, it's the same as 6 times what? Right. 1,000. I don't really care about the over 1. But here's what I want you to see. When we divide by a very, very small number, we end up multiplying by a very large number. So if you have a small denominator, that's going to give you a large value. So this is like 6,002. And you can see that as x gets closer and closer and closer to 3, the denominator is going to get smaller and smaller and smaller, which means the overall fraction is going to get larger and larger and larger. So what we would say here is that the limit, or here's what I would say actually, limit as x approaches 3 from the right of 2x over x minus 3 is going to be 6 over a, here's what I like to write, a very, 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 very small, slightly positive number. And a positive number divided by a positive number is a positive number. And since the fraction has a very, very small denominator, it has a very, very large value. This limit does not exist, but we are going to be more informative to the reader and tell them that, yeah, this limit doesn't exist. And also this function gets very large the closer x gets to 3 from the right. And then just to be complete, I know I'm with 30 seconds over, I'll just say that if we approach 3 from the left-hand side of the same 2x over x minus 3, now the numerator is still close to 6, but the denominator is very, very, very slightly negative. We're still going to get a very, very large number, but it's going to be a positive divided by a negative, which is going to be very, very negatively large. Again, this limit also doesn't exist, but we're telling the reader, yeah, we know it doesn't exist. And also, if x gets really close to 3 from the left-hand side, the function happens to get very, 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 very negative.